then it should wait for a couple of minutes.
Oh. Well, we can probably start.
Yeah. Okay. Very good.
Okay, so let's get started. Yesterday I forgot to tell you what we are doing this week. So this is part one, the many-body computational challenge. Yesterday we started with an introduction and we talked about iJulia a little bit. Today we're going to be looking at quantum spin chains. We're going to be diagonalizing Hamiltonian for the Ising model on quantum Ising model for spin chain. And then tomorrow, if we have time, we'll talk about statistical partition functions. There is a question mark here. We will see how the tutorial goes today. And then on Thursday, definitely, we'll be talking about the free fermion formalism. Very good. So what's the goal? What are the goals for today? Today, we have two goals. One will be to build and diagonalize a Hamiltonian for n spins, it's a quantum spin chain. And the second goal would be to actually extract universal information of a quantum phase transition. Okay, so that's what we want to do. And when I say today, I actually mean this lecture plus the tutorial. Okay, so the material that we will discuss this morning is something you have to apply this afternoon. So let's get started. First thing is, during this lecture, we'll learn how to build, using iJulia, Hamiltonian. And this Hamiltonian is going to be the one we discussed yesterday, the quantumizing model. With a transverse magnetic field and with periodic boundary conditions. So we'll connect the first and last spin in this way. So this is periodic. And at the end of the class, of the lecture, we'll see also anti-periodic boundary conditions. So we'll see how to, in about 10, 15 minutes, we'll see how to actually build this Hamiltonian using Julia. But we will also look at the translation operator. Okay, this translation operator, diagrammatically, what's going to do is we'll start with our spins, and it's going to take the first one to the second position, second one to the third position, and so on. And the last spin will come to the first position. Okay, we'll translate in a circle. And what this operator, so we're going to also build this operator. So let me call for spin n, for spin in position n, we have a basis of states in that vector space, two-dimensional vector space, where this Sn could be plus or minus 1, if in the sense that we'll have the sigma z acting on site n, when acting on one of these states, it's going to produce. These states are eigenstates of sigma z, okay? And when we call plus or minus 1, we could also denote by 0 and 1, and we'll actually be using this parity here later on. It's a choice of labeling, how you want to label the eigenvectors of sigma z. Good. And so acting on such a basis for S1, S2, S3, Sn minus 1, and Sn, what this operator does is it produces Sn, S1, S2, S3, Sn minus 1. Okay, it takes the last bit of information to the beginning of the chain. All right, very good. So, and then finally, we also need to introduce a third operator, which is going to be the spin flip Z2. So Z2 symmetry operator. S, and it is nothing but the product of sigma z's. Okay. And in the tutorial, you'll be asked to show that these three operators that we have, the Hamiltonian, the translation, in the tutorial, you'll be asked to show that these operators commute. Okay, translations, Hamiltonian, and symmetry operator. Yes?
So the spin flip operator should be composed of sigma x.
Right, so it's spin flip if you think that the spins are pointing in the x direction. You're right. Don't give. This is just to say that there are many ways of representing a Z2 symmetry, and this one has to do with flipping the spins, but indeed it would be in the x basis. If you were working in the x basis, the sigma z would flip the spins. Yes, you're right about that. So maybe that's not the best name you can find, but I'm just making sure that we talk about the symmetry that is acting on the individual spins. That's why this comment. Very good. So if you can. You will show that this is the case, that the Hamiltonian is the same when you translate the spin chain, but also the symmetry operator commutes with translations and with the Hamiltonian. And so what this means is that we can choose an eigenbasis. We can simultaneously, so it follows that we can simultaneously diagonalize the Hamiltonian, the translation operator, and the symmetry operator. And we're going to choose, so we're going to call the simultaneous eigenvectors. We're going to call them directly by the label them with the eigenvalues by these operators. So we'll have energy, momentum, and parity, what I'm going to call parity. And basically, what this means is that Hamiltonian acting on this operator, on these states, or this eigenvector, it's going to give us the energy. And then if we act with the translation operator, what it's going to do to this state is that it's going to produce a phase given by precisely this momentum. And similarly, if we act with the symmetry operator, it's going to produce a plus or minus 1, depending on this value of p. So here what I'm saying is that this momentum goes between minus pi and pi. Okay, so we get some phase here. And so we have this constraint, and then the parity is 0 or 1, okay? Which means S, the operator S takes the value plus or minus 1, depending on whether we have a plus 1 or a minus 1, okay? Very good. So shortly we'll go and use iJulia to produce these operators. And now I want to go to the second goal. I want to describe some theory attached to the second goal of today, which is extraction of universal information for a quantum phase transition. And what we have is this, so that's part B. We'll see indications that indeed at h equal to, when we choose magnetic field, transverse magnetic field equal to 1, something happens. We'll see that in the spectrum of the Hamiltonian. And what happens actually is that there is a quantum phase transition. That's a phase transition at 0 temperature. And what we have there is that the low energy long distance properties of this spin chain for h equal to 1 at criticality are described by a conformal field theory. Okay? And specifically what we have is the Ising CFT. And I don't know how many of you know about CFT, but don't worry, it's not, I'll just describe a few facts that we need to know. And this, or if you want, you don't even need to know this, but it helps to be able to relate subjects. So this is a minimal unitary model with central charge equal to 1/2. And it turns out that for so what we would like to do now is we would like to study our spin chain and extract information about the conformal field theory. Okay, conformal field theory is a theory in the continuum. It's usually attached to an infinite system. What we're doing here is instead of a continuous system in the thermodynamic limit, instead of an infinite continuous system, we're studying a finite system and on a lattice. So this is a very different type of system. But nevertheless, we'll be able to extract information about the conformal field theory. So, so how do we characterize a conformal field theory? So now this is a fact. A CFT, okay, is completely specified by what's called its conformal data. Okay, plus the conformal group acting on the theory, and those who are following Pedro Vieira's class, I think he'll tell you more about these things at some point. So what is this conformal data? You have to think of this conformal data as what specifies the universality class of the phase transition, of this quantum phase transition. Okay, so if we manage to extract this conformal data from the spin chain, we'll know which phase transition we're talking about. That's good. And so specifically, what is it that this conformal data consists of? We have a list of what's called primary fields. I'm going to denote them as phi alpha. And those correspond to representations of the Virasoro algebra, for those of you who know about CFT. And so for these guys, what we have is conformal dimensions. So conformal dimensions H alpha and H alpha bar. And here we'll be talking about two related quantities. This will be the scaling dimensions, the scaling dimension of this primary field, which is given by H plus H bar, and also conformal spins. Okay, and these are given by H minus H bar. Okay, so this is some data. There is also, in addition to the conformal dimensions, we need to specify the operator product expansion coefficients, whatever. There is more to it. I don't want to go there. Because what's important for today is that we'll be able to extract these guys, okay, from the spin chain. Information about these universal properties. So what are the scaling dimension and conformal spin? If we were working with the CFT and we look at a two-point correlator, remember we're working in 1 + 1 dimension, so we've been talking about space, but there is also time. So the conformal field theory is naturally defined in 2 dimensions, space-time. And then what we have is, at least in the Euclidean version of this, is that if we look at the two-point correlator for these primaries, I want to give you attach some physical meaning to these two quantities that we are going to be able to extract. And the meaning is this, that if you look at the CFT, the field theory that describes the continuum long-distance properties at low energies of this critical spin chain, and we look at two-point correlators for these primary fields, they will have a very simple form. For two primaries, you will only get this to be non-zero if the two primaries are the same. And then here you'll have some two coefficients precisely given by the 2 times the scaling dimension, and then e to the I2 times conformal spin times some angle, where R is just the distance between the 2 insertion points. So what you want to think of this is, remember, I just said this is the plane, and so this is X, this is Y, and we're looking at the two-point correlator between some point XY and the origin XY. And there what we can do is we can ask how much is the distance to the origin, and also what's this angle, phi. And what I'm saying is that the scaling dimension and conformal spin determine how this two-point correlator depends on the distance. That's the scaling dimension, tells you how this two-point correlator decays with the distance. It's a power law. Sorry, it's an exponential. It's a power law with this coefficient. Okay, that's the scaling dimension. Tells you how fast the two-point correlators decay with distance. And the conformal spin tells you what happens if you fix the distance and you change the point. So if I change this point in this direction, how the phase of the two-point correlator changes. Okay, so there is this physical picture there. Very good. And let me just tell you before, let's see. We're almost done. So let's see. I want to take this one up. Oh, this one doesn't go. Oh, yeah, this one. So the last thing I want to mention then is that for Ising model, with periodic boundary conditions, we'll be seeing scaling dimensions and spins for, well, let me tell you first what the primaries are. There is one that is called identity, and it has scaling dimension 0 and conformal spin 0. So in this table, I'm just telling you what happens for the concrete case of the Ising model. There is another primary field, so primaries. Let's call it primary field. Identity, spin, so-called spin, and then there is energy density. It's called energy density, nothing to do with the Hamiltonian. And this is 180 and 10, okay? Just, table. We'll see how we can recover actually this information. And there is also with anti-periodic boundary conditions, periodic boundary conditions, we'll see that we have 3 more guys that appear, which are, in some sense, non-local primaries or non-local scaling operators. And so these 3 guys, let me get them here. One is the disorder operator, mu, and has scaling dimensions 1h and conformal spin 0. And then the fermions, there will be 2 primaries called fermions, psi and psi bar, and they have scaling dimensions 1/2, and the conformal spin is 1/2 and minus 1/2. So this table, you'll be able to extract it from the Ising just by analyzing the Ising model spin chain. Very good. So what is the theoretical result that we're going to use to extract this information? Have to go to the 80s. John Cardy and also other people, they established a clear connection between a finite spin chain so imagine you have then this finite spin chain, okay, with n spins on this side, and on the other side we'll have the CFT, and we'll have the scaling dimensions and right. So we have these scaling fields, and these scaling fields, what they are primaries plus what's called their descendants. And again, if you don't, if you've not done CFT, don't worry about these names. So the connection is this: that if I look at the low energy spectrum, so that's what we called before energies and momentum for the chain. And if I plot it, I'm going to plot schematically the energy with as a function of momentum. Remember, we'll get eigenvectors, simultaneous eigenvectors of the Hamiltonian and the translation operator, and they'll have these eigenvalues. If I do that, say for the Ising model, I'll get some point here, some point there, some other point here. Okay, and it turns out that there is some structure to it. I'll get another point. Let's see how I do this. So basically, I get a number of points. Okay, another one here and here, and then I'll get one here, and so on. Okay. And if I go and now I look at the scaling fields, okay, so which come with also pairs of now scaling dimension and conformal spin. Okay, I gave you a table with some of these values there. So I'm only representing periodic boundary conditions, and it turns out that I'll see a very similar structure of pairs of scaling dimensions and conformal spins, and that's going to look like this again, and then maybe this one, and so on. Okay, so there is definitely a connection between the low energy spectrum and the scaling dimensions and conformal spins. And here I'll have a 0, 1, 2, minus 1, minus 2. This is going to be 1, 2, and so on. And so actually, the relation is expressed in the following way. We'll say that the scaling dimension, that the energy of a low-lying excitation is going to be equal to some non-universal constant plus another universal constant divided by the system size. Okay, and the scaling dimension alpha minus c over 12 plus order 1 over n squared corrections. So let me highlight this before we lose it. Okay. So this is 1, and then the momentum is equal to, and now just some rescaling of the conformal spin. Okay. So there is a lot of theory that goes into this result. One is something called operator state correspondence of the CFT that relates operators in the theory with states in the theory, and then also some map from the plane to a cylinder, which relates the infinite theory with the theory on a finite cylinder. We don't go through this. This course is not about CFT, but I'm saying there are 2 important results that lead to this connection, and this is the connection we're going to use today to extract this information by looking at the spectrum. Okay? Question, please?
What are A and B and the upper formula for the energy?
What are A and B? So actually, if you think about the Hamiltonian, when I give you a Hamiltonian, if I add the identity to it, nothing happens. I mean, you still have the same spectrum, right? And if I multiply the Hamiltonian by a constant, you still get the same spectrum up to rescaling. So what I'm saying is you can shift the spectrum, you can shift the spectrum by adding the identity. You can rescale the spectrum by multiplying the Hamiltonian by a constant. And so when you get the Hamiltonian, you don't know that you got it in the right way. So this A and B, these non-universal constants here, correspond to this, to the freedom that you have in rescaling the Hamiltonian. Thanks for the question. So very good. So the important thing, though, is that in this expression, this is universal. This is the central charge. I won't discuss it here, but it's also universal. And this is universal. Okay? And so the only things that are non-universal are A and B, and also N, the system size. But we know what the relation is between the energies and the universal property in terms of this system size. So we'll be exploiting that. Very good. So we are ready to go to Julia. Now we're going to, yeah?
What is the U and psi? I mean, what is the U and fermion field?
Yes. So I'm saying that in addition to the primary fields that we have here, if as we will do later today, if we discuss anti-periodic boundary conditions, so this was for periodic boundary conditions. If we switch to anti-periodic boundary conditions, then the spectrum will change, and we will see that the spectrum is organized according to other scaling dimensions and conformal spins, which will actually correspond to other primaries, which are non-local in some sense. We can discuss this later. But yes, the idea is I just wanted to give you a complete table, but indeed the subsequent discussion only referred to periodic boundary conditions. The example I draw there is for periodic boundary conditions. There will be the analogous analysis also for anti-periodic boundary conditions, and that's where we will see the disorder operator and the fermion operators. Okay?
What is the anti-periodic boundary condition?
It will mean that we'll take that Hamiltonian up there, and when I said periodic boundary conditions, that term will change the sign. Instead of a minus, we'll put a plus in there. Yeah. But we'll do this only at the end of today, so let's focus first on periodic boundary conditions. Okay? And do you all have your notebook ready? Now it's a good time to get it ready. If you don't, we have a minute because we need to get the projector started. I think the trick from yesterday of switching those lights, maybe Marcus, our specialist, can do the trick again. Okay, yeah, that works, but I'm going to actually be using the blackboard as well, so a bit of light would be good. Okay, then stay away from it. I think, is that okay? Can you see the blackboard reasonably well? I guess we have to compromise a little bit. So this is what? Julia 2. So this is the notebook that you hopefully received yesterday. Did you all receive the notebook yesterday? You didn't receive the notebook yesterday.
Like the portal was. Actually, the portal is already.
Okay. Is the email down?
Well, I put it on the wiki.
Yes, but they say the portal is down. So can you send it by email?
Yeah, I did this what I'm trying to do.
Or maybe I can do that myself. I don't know. So how many people do not have this ready?
I just got it.
You just got it? Oh, you can email it to it. Okay. So everybody.
Well, I have sent an email.
Okay. Okay. So at this point, does somebody not have the notebook ready? Very good. So we can start. So what is this? Second notebook. Let's start here. No surprises there. We can define sigma x and sigma z, an identity and xx. So what we're going to do is the first goal of today is to actually build this Hamiltonian that we've been discussing. And so how are we going to build this Hamiltonian? Well, what we're going to do is we're going to use some recursion here. If these circles denote the sides, remember that this Hamiltonian has two pieces. There is an x term connecting each side. And then there is a magnetic field acting also on individual sides. And we'll worry about the boundary conditions later. So the idea is that if we go from n spins to n plus 1, okay, I'm going to draw now an extra spin. I add an extra spin. These Hamiltonian terms are also in the new Hamiltonian. But what do I need to add? Well, I need to add an xx, connecting the last spin with the new one, and a sigma z at the end, right? So in going from n to n plus 1, what I need to do is take care of these two terms. So this is what we have under let us build the Hamiltonian for n spins. What we are going to do is first, H will be the Hamiltonian on two spins only. Okay, we put the xx term and also magnetic field on the two spins. That's what this line is doing, and we did this yesterday, so no surprise there. And now we are going to iterate from n equal to 3 to total capital N. What we're going to do is we are going to add one spin at a time. Okay, so inside this for loop, what you see is that what we're doing is first, in going from here to here, we'll take the Hamiltonian that we have, and we'll do the Kroneck. We'll tensor it with the identity on the new spin, right? These Hamiltonian terms should only act on the first n spins. Okay, so we tensor it. We tensor all these terms that we already have with identity. That's the first term here. Then the second term says, all right, let's introduce this Hamiltonian term, the xx, connecting what used to be the last spin with the new last spin. Okay, and that's accomplished by putting identities everywhere else. So this is this I produces the identity on dimension 2 to the n minus 1, n minus 2, which means that this is all these spins. Okay, we are producing at this point. We have, so if now we have n spins here, then here it's n minus 2. And so the identity on these spins is dimension 2 to the n minus 2. So that tells us this term here. We are just introducing the last xx term in the Hamiltonian. And finally, we are going to introduce the third term in this expression refers to the magnetic field on the last spin. And again, if here we have n minus 1 spins, we produce the identity I of dimension 2 to the n minus 1 times, or cron the sigma z. Okay? Are there questions about this construction? So what's missing to finish the Hamiltonian? Boundary term, the last term, and this is what this term here is doing. Okay? Is putting x identity on n minus 2 spins times x. Okay? Very good. So if you shift n to this, and there was a capital N equal to 3 there, you'll produce this Hamiltonian, which happens to be the right one. Now, there is a warning somewhere. It says don't try this for very large n. Okay? Because, I mean, you can try, but then you'll have to restart your laptop. It's not worth it. So I tried this with n equal to 14, and it would still work. You don't need to try it. But n16 seemed to be already beyond reach. We're going to be working with n equal to 3, 4, 5, at some point 10. So we'll not reach those limits. There is no point, no need for that. Okay, so now what we want to do, now that we understand how to build a Hamiltonian, we want to build our first, I think it's our first function with Julia. So that instead of having to type all these instructions every time we want to build a Hamiltonian, we'll just call the function. So what we have here is we create a function by writing function and then the name of the function and the arguments that will go into it. So we'll introduce the number of spins and the magnetic field. And basically what we do inside the function is to create this Hamiltonian that we just described. Okay? You identify the loop that we just described. This is just the boundary term. Okay, and then we can call this function, once we have introduced it, we can call it by just say build h, and then for n equal to 3 and magnetic field 1. And if we do that, and everything is fine, then we should be recovering exactly the same Hamiltonian that we just produced before. Okay, so great. We have a function. Now let's exploit that. So what we're going to do here, and I don't want to spend too much time, is on this is to just try this to see that it makes sense. We're going to produce the Hamiltonian h for n equal to 8 spins. That's the first line there, n equal to 8. Within a range of magnetic fields, so we'll have a loop again. This loop will allow us to explore 21 different magnetic fields, ranging from 0 to 2. Yes?
So I have a question. H val. This is an array, right?
Yes.
So
it's some array, yes.
Yeah, so the sum array. Does the numeration start from 0, or it starts from 1?
I don't know. Wow. I mean, there is a hint here, right? But start from 0.
From 0,
where the labels?
Yes.
The labels start from 1.
From 1.
Yes, yes. Okay, yeah, sorry, I thought, right. So the values inside this array start from whatever you're writing here, 0. Okay. It goes from 0 to h max, which is 2, and it takes steps of delta h, which you choose conveniently so that you have in total 21 different values. But let's not discuss this. I mean, yeah, good question, but let's not focus on this. We can discuss this in the tutorial if you want. My screen is jumping. I don't know what that means. Very good. So what I want to point out from this piece of code is that we are going to just build a Hamiltonian for 8 spins and for whatever value we have of the magnetic field in this collection. And then we'll diagonalize the Hamiltonian, and we'll look at all the energies, and we're going to store the energies. Okay, I don't know what's happening with the screen. So the energies, I've initialized these 2 to the n values. This is a matrix of zeros. I've initialized it here. There are 2 to the n. So space, this is a matrix with 2 to the n times 21. Okay. So for each magnetic field, we'll store here all the eigenvalues of the Hamiltonian. Okay. And so that's what we do in this line. For the current value of the iteration, we'll store all the eigenvalues. D contain the eigenvalues of the Hamiltonian. All right. So let's do this. Shift Enter this one. And now we have produced these energies. We just didn't do anything about, we haven't shown them. But let's directly plot them. Okay, so for that, we're going to be using pyplot again. And basically, yeah, I want you to directly play with this instead of me trying to describe carefully what all these instructions mean. Yesterday, when I saw that my figure didn't fit in the screen, what I did was I went back and started using this first line here. This title doesn't show anywhere, but this fixed size statement allows me to decide the size. So 8 refers to the width, 3 to the height, and thanks to that, now we can plot the result in a way that it fits in the screen. Okay? So we can even push it a little bit more. So let me change this to 4. Now it's a bit higher, okay? All right, so what we see here is, as a function of the magnetic field, we plot the spectrum of the Hamiltonian. So these are the different energies in this direction. And we see that as we change the magnetic field, we can follow the lines. And the point of showing this plot is first you get some code, sample code, how to produce a plot. But also, if you look roughly at around magnetic field equal to 1, you see that something interesting happens. Here we actually have 2 energy levels which are essentially the same. And roughly at h equal to 1, they split into 2. Okay? And this this is an indication that something is happening at h equal to 1. That's precisely the critical point. Okay?
Well, for n equal to 8, it takes much time to plot.
To plot. No, that's because you have the using plot, pyplot. That command needs to initialize. If you try again, it won't take that long. Very good. So this is a clear indication that there is a critical point. Or if you want, we knew that there is a critical point, and you can see that something indeed is happening at h equal to 1. And so what we want to do next is to study this critical point at h equal to 1. And so for that, what we will need to do first is we already built the Hamiltonian, so now we'll build a translation operator. Okay? And this translation operator, let's see, you go up, and you come down. Okay, so this translation operator, T, we already described what it does. And now what I want to point out is that if n was equal to 2, this translation operator is just permuting the 2 qubits, the 2 spins. 1, 2 become 2, 1. If n was equal to 3, what we would be doing is this 3 sent here, 1 comes here, and 2 comes here. Okay? So, but this is nothing but the composition of these 2. Okay? So here I'm going to send 1, 2, 3 to 1, 3, 2. Okay? And then I change these 2. So what I'm saying is that by multiplying these 2 operators, we will be done. And in general, well, let's do n equal to 4. We can see that in general, if we already had n equal to 3, which looks like this, and we wanted to produce n equal to 4, which should look like this. So 1, 2, 3, 4 is mapped into 4, 1, 2, 3. This thing is actually the same as doing the following. Composing, again, a single swap of 2 spins with the n equal to 3 case tensor identity. Okay? So again, in going from n to n plus 1 spins, what we need to do is we can reuse what we had for n, tensor identity, and then identity tensor the swap for 2. So this is exactly what this translation operator, how this translation operator is built. Okay? Just there is a loop over the number of sites. And you have produced at the previous step something like this, and now you produce also something like that, and you multiply them together. That's what this function is doing. Okay? Very good. So, and finally, we also need to build the, what is this? The spin operator. Okay, so actually if you shift, if you shift enter that, the translation operator, you'll see an example here. You could change to do this for 2 sides, and you would have a Q 4 times 4 matrix, and so on. Very good. And the symmetry operator, there is not much that we need to say about it. It's simply the product of sigma z's. And so you can again realize that if you had it built, if you build it for n minus 1, and you want it for n, you just multiply by sigma z, okay, on the new spin. And so that's what this function is also doing. Okay, so now let's look at more interesting things. So let us try to actually, what we would like, remember, what we are trying to do here is we want to diagonalize simultaneously these 3 operators, H, translation, so the Hamiltonian translation and the spin flip or the symmetry operator. We want to obtain these simultaneous eigenvectors of all these 3 operators, okay? So how are we going to do this? Well, we're going to call a function that diagonalizes matrices. We're going to produce H. This is here. We produce, for n equal to 10, we produce H, T, and S using the functions that we have just described. Okay, so we build these 3 matrices. They are 2 to the n times 2 to the n matrices. And then we're going to call a variation of the AIK. Remember yesterday we used AIK to diagonalize the matrix that we put as the argument. So we're going to call a different matrix, which is AIK S. S stands for sparse, and which has an extra argument, this one here, which allows you to select how many eigenvectors and eigenvalues you actually want. Remember, this is a 2 to the n times 2 to the n matrix. It could take a long time to diagonalize. But in the end, we're only interested in the low energy spectrum. So we are only interested, say, in this case, in 12 states, okay? I'm keeping 12 states.
So this NEV, is it some kind of parameter?
Yes. So actually, I should have written something different here, which is, okay. Hopefully it still works. Yeah, ignore what happened. So, so this is the way we have to we can use to specify how many eigenvalues and eigenvectors we're asking the function x to compute for you. Okay. And what did I put in the middle? Well, here what I did is the following. If I just give the Hamiltonian, the Hamiltonian is degenerate, right? It may be degenerate. May have, may have 2 eigenvectors with the same energy. But I want to find the simultaneous eigenstates of all these 3 operators. So what I do is I take the Hamiltonian, and I also take the translation operator and the spin, the symmetry operator, and I put them there in some way to build a matrix, which, of course, just think about this. These operators all commute with each other, right? So I can put a matrix which is a linear combination of those. Or also I can multiply them. I can do many things. The important thing is that the eigenvectors are not going to change. But I'm going to break the possible degeneracies that I had there. So what I'm saying is, if I have this, let's see, where do I do this? If you give me 2 matrices, and I'm just going to write them in diagonal form directly, this matrix, and also this matrix, I know that they can be simultaneously diagonalized, so let me write them directly in diagonal form, right? Let me put a 2 here. So if I diagonalize this one, there is this subspace of eigenvalue 1, and the function that diagonalizes this will not know that I actually want a concrete choice of eigenvectors here, right? So it will be a linear combination of these two, any linear combination. But if I now take a linear combination with this other matrix, the sum does no longer contain, if I look at the sum of these two matrices, then I have a 4 here, a 3, and a 4, okay? So what just happened is that these two are no longer degenerate. But of course, now another degeneracy has appeared here. So I need to play around. A trick is that if I know that these two guys have order 1 eigenvalues, or the separation between them is order 1, if I put a small coefficient here, right, now I'll be breaking the degeneracy. So that's 1.3. This is going to be 1.2, and this one is going to be 2.2. And now that is, I've completely broken the degeneracy. So if I diagonalize this matrix, I'll get eigenvectors that are simultaneously eigenvectors of this matrix and the other one. So this is just some trick. You can play around what coefficient you have to put here. I don't know. Just play around until you find one that breaks the degeneracy. Very good.
You subtract the whole part and I with that power from the Hamiltonian.
Right. Very good. Thanks for asking this. So that was the next thing I need to explain. X will give you the lowest eigenvalues and corresponding eigenvectors. But how do we find lowest? So for instance, in the spectrum of the Ising model, we just saw that it was a bit complicated here. What we have is that this line, roughly this line here, corresponds to 0 energy. And we decided that we want these guys, okay? So the most negative eigenvalues. But these functions, what they can give you, for instance, is the eigenvalues with the absolute value, largest or smallest, right? So what we do is we actually take what we are going to do is we're going to achieve the whole Hamiltonian down to make sure that this is not, that these guys here have the largest absolute value. That's what we achieve by subtracting some amount proportional to n. Okay? This is something that has been designed in such a way that we've shifted the spectrum of the Hamiltonian such that now the low part of the spectrum corresponds to has the largest absolute value. Very good. So, and we have to remember that we did that. So later on, we have to actually put this 4n back into the spectrum. Okay. Very good. So this plot was just to show that. So what did I plot here? After all this, we look at this matrix that we built here. We're diagonalizing this matrix. And we plot the eigenvalues, the imaginary part versus the real part. And we get a plot like this. So I was just checking. We asked for 12. We asked for 12 eigenvalues. And I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. 9, 10, 11, 12. So I hope there are 12, no? Yeah. No, there are 10.
There's some missing.
Two down.
Oh, thanks. So there were 10, huh? Okay, 12. Okay, yes. So this was to check that we have indeed broken the degeneracy. We asked for 12 eigenvalues, and we got 12 different complex numbers, okay, imaginary part versus real part, that are not the same. So we have broken the degeneracy, if there was any degeneracy, okay? If you actually only diagonalize H, you would suddenly realize that these two guys have exactly the same energy, those two guys have the same energy, and so on.
So if there is degeneracy, does this function have difficulties working?
No, it's not that it has difficulties. It's that if you give me, in this subspace, say energy equal to E, right? You have two eigenstates with that energy. This function will give you any linear combination of these two eigenstates, not precisely one the linear combinations that also have a well-defined momentum or parity. So that's what we're trying to fight here. We want eigenvectors which are simultaneous eigenvectors, not just of H. I mean, eigenvectors not just of H, but also at the same time of T and S. Very good. So now we know how to do this. We know how to find the simultaneous eigenvectors of H, T, and S, of the Hamiltonian, the translation operator, and the symmetry operator. And now what we want to do is, once we have those simultaneous eigenvectors, we want to read off how much is the energy, how much is the momentum, and how much is the parity. Okay? And I can tell you already there is a mistake in this expression, and you have to find what the mistake is. But what we do here is remember that we had this. Let me first comment this out so that we can see all the relevant expressions in just one single page or on the screen. So what we have here, if I put this at the end, it just doesn't show the last expression. Yes?
You said that to break the degeneracies, we should add a little bit of T and S to H, but now we're multiplying.
Yes, yes. You try your favorite trick. So the goal is to break the degeneracy. Yeah. You have these matrices that you know that they commute, so you can multiply them, add them in pieces, whatever works for you. Okay? This is not the way to do it. It's just a possible way of doing it. What you need to remember is that these matrices can be made diagonal in the same basis. There is a basis for which all the matrices are simultaneously diagonal, and therefore multiplying them produces another matrix which is also diagonal. Adding them produces another matrix, right? There is a subalgebra of size.
But this changes the eigenvalues, doesn't it?
It does change the eigenvalues. The only thing we're getting out of there, the only thing that we're going to keep are the eigenvectors. And exactly what we are going to do now is we're going to look for the eigenvalues of H, T, and S. Okay? So in this expression here, we're only going to keep U. D is indeed eigenvalues of this mixture that we created. Now we want to look at eigenvectors. And so remember, the eigenvectors are in this matrix U. The columns of this matrix U correspond to the eigenvectors. So in particular, what I call here psi is going to be the first column, okay? The first column of this matrix. And this expression here, what it's doing for you, it's computing the expectation value of the energy, okay? Is that clear? So we're computing now psi H psi. That's what this expression is computing. But remember that this thing here is an array. The result is a 1 times 1 array. So we add this expression to extract the number. And just in case things got a bit numerically, this should be just a real number, but there will be some zero imaginary part. So I want to get rid of that. So I ask for the real part of this array, and then I extract the number. Okay? So this is the energy. But actually, this is not the energy, right? Because we did something to the Hamiltonian. So this is the mistake that we need to correct here. So the actual energy is not this one, but this one plus 4. And I usually put the multiplication, but you don't actually need to do that. Okay. So the actual energy is written down here, and it's this number, minus 12. That will be for the ground state, if this happened to be the ground state. So you see, we've extracted the energy. We can also similarly extract the momentum. What we need is to take this. What we're going to do is we're going to take psi t psi, right? And this is supposed to give e to the I k. for the momentum k. And so what we do now is, this is a complex number, and this function here, angle, extract the phase of the complex number. So when we take angle of this expression, what we get is directly k. Okay? And again, k, we just want to extract the number. So we put this, right? This is a 1 times 1 array. We just want the number. There is actually no need for real here. We can remove that. Finally, for the symmetry, yeah.
So k is equal to real k, and then we put 1 in square brackets. So what k is an array then?
Sorry?
Is k an array?
At this point, k is right. At this point here,
Yeah.
we've created an array. Okay. So let's play with this. We can copy this. Then we go to insert cell below. Now we have a new cell. And we can do this. We can just copy this there. I'm going to comment out the first part. Okay. And if we shift enter this, whoa. So I lost it. Where is it? Above?
Yeah.
Here. So at this point, what you see is that you have a one-element array with the number being 0. And here, actually, because it's a real, I can remove this. I don't need this part. So let me remove it. And so at this point, we'll just get the element in the array. Okay? And if we, so let me show you what actually happens. Right, no, that's fine. That's good. Okay, so that's there. I'm just gonna remove this new cell by cut cell. These scissors are very useful. Okay, so and finally we do the same with the parity. So this expression here, we're just computing psi, symmetry operator psi, and this should be equal to plus or minus 1, depending on the state that we have. And then what we do is we extract the number. Okay, so we get plus or minus 1, and we subtract 1 to it. So what do we get? It's 0 or minus 2. Divide by 2. So we get 0 or minus 1. And we put a minus sign, so we get 0 or 1. Okay? So we went from plus or minus 1 to 0 or 1 as we want. Okay? And then we can print the result, and that's what we had here. Okay, so what we've learned is, first, we've learned to find the simultaneous eigenvectors of all these matrices by putting a convenient combination of these matrices and calling Ix. That gave us, in this case, the 12 first eigenvectors. And the second thing we've learned is, once we have these eigenvectors, how to extract the eigenvalues. Okay? And that's the expressions that you have here. You build the eigenvector, and you sandwich the operator H or T or S. Right? This gives you a 1 times 1 array. We can extract that number out of it, and maybe we want to process it. In the case of the momentum, we take the angle of the complex number that we got. In the case of parity, we take this simple function to transform a plus or minus 1 into a 0 and a 1. Very good. So, oh, that means it's time. OK. Hi, Pedro. All right, so the rest of here just contains, oh, Pedro, you'll enjoy this. Sit down. So, no, what I have, we're almost done. So what I have here is sample code that will create nice plots for you, meaning plots that describe the exact scaling dimensions. This is a plot of conformal spin versus scaling dimension versus conformal spin for the operators that you would get in the CFT. And then in this afternoon, you'll have to complement this plot by putting the numerical results that you obtain from the low energy spectrum of the Ising model. Okay? You can do this for the periodic boundary conditions, for the anti-periodic boundary conditions. So basically, again, this is just sample code that you can reuse Okay, you just have to understand that this part here. So what we're doing now is we're creating two subplots, not just one plot, two subplots next to each other, and this is the information that you have to input to get the subplot, the second subplot, where the x-axis you want -3 between -3 and 3, y-axis labels. You want a label for the x-axis, y-axis. So you basically can copy-paste this and use it just by changing the content whenever you want to create a plot. So it's just sample code, no big deal. We don't need to go carefully through it. All right, and then finally, what I did here is I gave you an upgraded version of the functions that create H and T, the Hamiltonian and the translation operator, so that we can also account for anti-periodic boundary conditions. Okay? Remember that what I said is that you see the Hamiltonian up there has a minus sigma x and sigma x1. So if we want to put a plus instead, well, it just corresponds to going to the last term that creates the Hamiltonian and put a BC, this is a variable, that contains the boundary conditions. It's set to 1 by default, but if you specify it when you call the function, if you specify the boundary conditions, by explicitly putting a +1 or -1, you'll decide which boundary conditions you have. And the same thing for the translation operator. It turns out that if you have the translation operator with anti-periodic boundary conditions, this translation operator does no longer commute with the Hamiltonian, but you can fix it. You can produce a translation operator for anti-periodic boundary conditions. And again, the trick is that somewhere you add a minus sign. So I don't even see where it is. BC, do you see some BC somewhere? Right, so if this is -1, then you have to actually add some spin flip, what we call a sigma z on the first spin. Okay, so whatever, you'll see this in the tutorial. Okay, very good. So we're done. Are there questions? Okay, so I'll see you in the tutorial. We'll use all this afternoon. Very good.